Welcome to the Explainer. Today we're doing something really cool. We're basically building a virtual wind tunnel right from the ground up. We're going to dive deep into a powerful computational method to figure out exactly how a wing generates lift, and we'll be using a classic aerodynamics report to guide us.
Okay, so let's get right into it. The big question is, how can a relatively simple program actually predict a wing's lift with any kind of accuracy? We're about to walk through how to translate all that complex physics into a simulation that really works.
All right, first things first, we have to simplify the problem. I mean, simulating every single air molecule is just not going to happen, right? It's impossible. So we turn to this classic idea in aerodynamics called thin airfoil theory. It makes the whole thing manageable.
Now this is a really clever trick. Instead of dealing with a solid, thick wing, just imagine a sheet of tiny little whirlpools, we call them vortices, all lined up along the wing's centerline, its camber line. This lets us capture the lift-generating magic without getting bogged down in all the messy geometry.
Okay, so we have this idea of a smooth, continuous vortex sheet. But how do you tell a computer about something that's continuous? That's where the lumped vortex method comes into play. It's this awesome numerical technique that's perfect for airfoils with complex shapes where, a simple formula just won't cut it.
The algorithm itself is actually pretty beautiful and logical. As you see here, first we chop up that camber line into a bunch of separate little pieces, or panels. Then, on each of those panels, we plop down a single lumped vortex. And here's the crucial part. Step 3. We enforce the physics. We basically tell the simulation, hey, air can't flow through the airfoil. And just by doing that, we create a system of linear equations that a computer can actually solve. We've turned messy fluid dynamics into clean algebra. How cool is that?
And honestly, it all boils down to this single, pretty elegant matrix equation. A gamma equals RHS. So A is what we call the influence matrix. It basically describes how every single vortex affects every single point on the wing. Gamma, well, that's a list of the unknown vortex strength. That's the treasure we're looking for. And the RHS, the right-hand side, that's just the incoming airflow. If you can solve for gamma, you've solved for the lift.
But as anyone who's ever coded anything knows, just having an equation doesn't mean you're home free. There's a potential glitch in our matrix, a big one actually. Trying to solve it directly can cause some serious numerical headaches.
The problem is that our matrix A can become what mathematicians call ill-conditioned. This happens a lot when you have panels bunched up near the edges of the wing. And what that means is that tiny, totally unavoidable rounding errors inside the computer can get blown up into huge, crazy errors in your final answer. The analogy of a wobbly camera tripod is perfect. The tiniest little shake in your picture is completely blurry and useless.
And yeah, the source report we're using points this out directly. It says a direct solution might produce unphysical oscillations. That's a fancy way of saying the results are complete garbage. They make no physical sense. So we obviously need a better way.
So to fix this, to tame our wobbly matrix, we need to pull out a bigger mathematical tool. And that tool is called singular value decomposition, or SVD. It's what's going to give us a much more robust, much more stable solution.
So, what is singular value decomposition? Think of it like a noise filter for our unstable system. It works by taking our matrix A and breaking it down into its most fundamental parts. It separates the really strong, important signals from the weak, noisy ones that are causing all the problems. By just filtering out those weak, noisy bits, SVD leaves us with a stable result that actually means something in the real world.
And this comparison here just nails the trade-off, right? A direct solver, yeah, it's fast, but it's brittle. It can completely fall apart on you. The SVD solver, on the other hand, gives us that robustness, that stability we absolutely need to trust our results. It's the key to getting a simulation that actually works.
All right, so we've talked a lot about the theory. SVD sounds great and all, but does it actually work? Well, there's only one way to find out. We got to put our code to the test and validate it against some trusted, real-world data.
And here we go. These are the results. We ran our simulation for two classic, super well-documented airfoils, the NACA 2412 and the NACA 4412. The whole idea was to see if our simulation's output could match the benchmark data from the legendary NACA Report 824. I mean, that thing is basically the gold standard for this kind of work. Okay, first up, let's look at the pitching moment for the NACA 2412. This is that natural twisting force on the wing, whether it wants to pitch its nose up or down. We're looking at it at a very specific spot, the quarter chord.
Our SVD models spit out a number -0.0523. So, how does that stack up against the historical data?
Well, the official benchmark value is exactly the same, -0.0523. A perfect match all the way out to 4 decimal places. This gives us a ton of confidence that we've built this thing correctly.
Okay, what about the zero lift angle? That's the precise angle where the wing doesn't produce any lift at all. Our model predicted -2.077 degrees. The benchmark? -2.08. The error is just 0.003 of a degree. I mean, that's practically nothing. It's an incredible match.
So what's the bottom line here? What are the big takeaways? Well, first, our simple implementation shows fantastic agreement with that historical data. Second, it correctly shows that the pitching moment stays constant, which is exactly what the theory predicts. And get this, we did all of this with just 100 panels. It really proves that SVD is a super robust and reliable way to solve this classic aerodynamics problem.
I mean, think about it. This code absolutely nailed data from a report written back in 1945. That not only confirms how solid our implementation is, but it also shows you the timeless power of these fundamental principles. And it makes you wonder, right? If we can model the past this accurately, what kind of modern problems can we tackle with these tools today? Things like designing hyper-efficient drones, or maybe even the next generation of aircraft.